Now, there's a whole class of power systems in which the working fluid remains in the gaseous state for the entire cycle. So we want to contrast that with, say, a Rankine cycle, which has steam transition from a superheated vapor even down to a compressed liquid. So we're experiencing two different states in those cycles. But in gas power systems, generally we use air or model the system using air and have this system or have this working fluid remain, of course, gaseous the entire cycle. And gas power systems, or these types of gas power systems, are convenient ways to model internal combustion engines. Now, in the truest sense, internal combustion engine sprays liquid into a gas and ignites it, so it's not sort of the purest form of a gas power system. But in any case, we can get some reasonable approximations and study the relative influences of different factors of internal combustion engines using some simplified gas power system models. So in this video, we're going to do a brief overview of some of the engine terminology that will be used later on in our analysis of gas power systems. So first, let's talk about the two principal types of internal combustion engines. And the first is a spark ignition engine, in which fuel and air are ignited by a spark. All right, and for those of you that are engine savvy, you'll know that this is, of course, what gasoline engines do. The second type is compression ignition, in which air is compressed to a high temperature and pressure sufficient to spontaneously ignite fuel when introduced. So we compress the air in the piston so much that the temperature and the pressure they get high enough that when we introduce diesel fuel, it ignites. So this is how modern day diesel engines work. All right, some general engine terminology. So this will include stroke, which is the distance the piston moves in one direction. The bore, which is the piston diameter. Top dead center. This refers to the cylinder volume at its minimum. All right, so that's when the piston is completely to the top of its travel and the cylinder or the space inside the cylinder is minimized. And of course, accompanying that would be bottom dead center. And that's where cylinder volume is at a maximum. the compression ratio is the ratio, and we'll denote this ratio as R, the compression ratio. That is the volume at bottom dead center over the volume at top dead center. So R should always be greater than 1. And then finally, the mean effective pressure, MEP. Let's go ahead and write that up here. Mean effective pressure, MEP. That is the theoretical constant pressure that, if it acted on the piston during the power stroke, it would produce the same network as actually developed in one cycle. So we'll go back to this idea of boundary work, PDV, right? So that mean effective pressure is that pressure that if it was constant and it acted over the change in volume between top dead center and bottom dead center, would produce the same amount of work as developed in one cycle of an internal combustion engine. And as we'll see in a bit, the pressure during one cycle of particularly a four-stroke internal combustion engine is quite varied. All right, so a four-stroke internal combustion engine has a cycle that looks something like this on a PV diagram. I would certainly recommend you consult your book for perhaps a better rendition of what this actually looks like. And they probably give you quite a detailed description of what each process is in one cycle of a four-stroke internal combustion engine. But let's think about it this way. Let's go ahead and assume that the start of the cycle is here, where combustion is initiated. Okay, so following the initiation of combustion, which happens when the piston is at top dead center, so it's at its highest most point, the pressure is going to increase and then push that piston down. And as that piston moves down, we're going to have an increase in the volume and then the eventual decrease in the pressure. So that's what's known as the power stroke. So that power stroke lasts from here all the way to this point here. And at some point before the end of the power stroke, our exhaust valve opens. Or really, I should say, the power stroke lasts from top dead center down to bottom dead center, at which point our exhaust valve opens. Okay, so now from here back down to top dead center, this portion here is the exhaust stroke. So now the piston is moving back up, pushing the exhaust gas out of the piston. Okay, so power stroke, exhaust stroke. At this point, at top dead center, the intake valve opens, and exhaust closes. Okay? All right, so this is now our intake stroke. So again, the piston is moving from top dead center to bottom dead center and pulling in fresh air. When we reach bottom dead center, boom, our intake valve closes. And from bottom dead center back up to top dead center, our last stroke is the compression stroke. All right. And during that compression stroke, we will also inject some fuel and then initiate combustion, boom, and start the process over again. So we have the power stroke, the exhaust stroke, the intake stroke, the compression stroke. This is not to look exactly like an 8, but little like a sort of a skewed 8, perhaps. But in any case, the takeaway is there are 4 different processes on this PV diagram, hence the term a 4-stroke internal combustion engine. Okay, the final topic of this video will be an air standard analysis. An air standard analysis is a sort of convenient way that we can put some simplifying assumptions on processes like this so that we can do nice closed form analysis of these different cycles. So just as we have assumed that some of the components in a Rankine cycle are ideal, which in real life they're not, air standard analysis sort of follows that same spirit. So what it allows us to perform accurate modeling of reciprocating internal combustion engines well, what I should say is the accurate modeling of reciprocating internal combustion engines requires computer simulation due to complexity. But the air standard analysis lets us get part of the way there. So it allows us to do some of these analyses on an elementary level. So these air standard simplifications, there are 4. The first one, we don't treat products of combustion as air and fuel. We treat the working fluid as only air and air as an ideal gas. And yes, I know I've put 2 L's in modeling, a product of living in Britain. I think it's become habit now. All right, the second air standard assumption is that the combustion process is replaced by heat transfer from an external source. So in a true internal combustion engine, the heat is generated by the ignition of these fuels. But in this air standard analysis, we're going to say, yeah, we're going to heat our gas, but we're going to do it from something outside the piston cylinder. Third, there are no intake and exhaust processes. Okay, so I'm not expelling my air and bringing in fresh air. I'm just using the same fixed amount of air for the entire cycle. And finally, all processes are internally reversible. All right, so there are my 4 assumptions. Let me do an air standard analysis. There is one modification to an air standard analysis called a cold air standard analysis. And a cold air standard analysis, it takes all the assumptions of an air standard analysis and adds one more, the assumption of constant specific heats. So in subsequent videos, we're going to see numerous examples of air standard cycles and use these assumptions to help us generate simple models for them.